In this lecture, we will be continuing our analysis of Taylor polynomial approximations. So recall, we're using Taylor's theorem, which gives us this scenario where you have f with derivatives of all orders on an interval I containing a. Then for each non-negative integer k and each x in I, we have this expression where f of x is equal to the kth degree Taylor polynomial pk of x plus the corresponding remainder term rk of x, where we have this form for rk. In the first part, we looked at problems where you're dealing with approximations. We use the Taylor polynomial pk of x to approximate the function f of x on an interval I with some error tolerance. And we noted that you can be given two of these and asked to find the third. So we looked at problems in the first part of the lecture where we were given the approximation, we were given the interval, and we were asked to find the error tolerance. But it's common to be given exercises where you're given two of these and you have to find the other. So we will look at the other two cases. We will look at the cases where we're given the approximation and the error tolerance we desire, and then we have to find what interval is that going to work on. In the other example, we will be given the interval on which we want to work and the error tolerance we need, and we'll find the appropriate approximating Taylor polynomial. So first, for what values of x can we approximate sine of x using x minus x cubed over 6 with an error less than 0.0005? Well, we note that when we're asked for what values of x, we are being asked, what's the interval? So in this case, we're given the error tolerance, we're given the approximation, and we have to find what interval is fair game for our values for x in this setting. And we note that this approximation is this here, what we would call P3 of x, the third degree Maclaurin polynomial for sine of x. Now you can use Taylor's theorem, but we also note that this series is alternating. Since it's alternating, the alternating series estimation theorem tells us that the error of our approximation is less than or equal to, in size, the first term omitted. Well, we know our first omitted term is x to the 5th over 5 factorial. Okay, let's think about our goal. Our goal is to know what are the values of x that we can use this approximation for sine of x and get an error smaller than 0.0005. Well, think about this theorem. The theorem gives us that the error is less than or equal to this first omitted term, an absolute value. But we can force this term to be smaller than the error tolerance that we seek. So we could set this to be less than or equal to 0.0005. And it's key to recognize that this is the inequality that we are setting. And we now focus on this inequality. If we choose our interval for x such that this inequality is satisfied, the alternating series estimation theorem forces the absolute value of the error to be smaller than 0.0005 by this string of inequalities. So we now focus on x to the fifth minus x to the fifth over 5 factorial in absolute value being less than or equal to 0.0005. Which we can write as the absolute value of x to the fifth over 5 factorial being less than or equal to 0.0005. Let's write 0.0005 as 5 over 10,000. And note, we should multiply both sides by 5 factorial. So we get absolute value of x raised to the fifth power is less than or equal to 5 over 10,000 times 5 factorial. We can then take the fifth root of both sides and maintain the inequality. And so we get the absolute value of x is less than or equal to 5 over 10,000 times 5 factorial raised to the 1/5 power, which means our interval is this open interval from negative 5 times 5 factorial over 10,000 to the 1/5 to positive 5 times 5 factorial over 10,000 to the 1/5. And this interval is approximately equal to negative 0.57 to positive 0.57. So, if we restrict our choices of x to this interval, our approximation of x minus x cubed over 6 to sine of x will always have an error less than 0.0005, as desired. What if we have an example where we have to find the approximating polynomial? So suppose we want to approximate cosine of x on minus 1, 1 with an error smaller than 0.0001. What approximation should we use? Think about this scenario where maybe you're fine-tuning some factory equipment, and in that fine-tuning you have to have cosine of x within 1 over 10,000 for x in negative 1, 1 for the machine to work properly. Well, since we're working on the interval minus 1, 1, 0 is the midpoint of that interval. So the Maclaurin series is a natural place to start. Let's use a partial sum of that Maclaurin series for our approximating polynomial. Well, we note that this is alternating. So the alternating series estimation theorem tells us that the absolute value of the error is less than or equal to the absolute value of the first term omitted when we use a partial sum of the series to approximate the series itself. We know our first omitted term will be x to some even power, let's call it 2n, over 2n factorial. And our goal is to find the first term to omit, which again will be either plus or minus x to the 2n over 2n factorial. Well, let's think about the idea of looking at a worst case for this. What's the worst case for this expression? We can rewrite it as the absolute value of x to the 2n over 2n factorial. We know we're working on the interval -1 to 1. So any x that we choose will be from that interval. And so we have this error being less than or equal to the absolute value of x to the 2n over 2n factorial. What's the worst case for this, given that x is in -1, 1? Well, we know the absolute value of x to the 2n is at its worst when x is equal to 1 or -1. Which simplifies to 1 over 2n factorial. Okay, so we know the error using the alternating series estimation theorem and the fact that x lives in the interval -1, 1 is at worst 1 over 2n factorial. Well, what did we want? Let's go back to the statement of the question. We wanted an error smaller than 0.0001. So let's set this to be less than or equal to 0.0001. So this is the inequality that we set to force our error via this string of inequalities to be smaller than 0.0001. So we now look at this inequality here on its own. We have 1 over 2n factorial less than or equal to 1 over 10,000. Let's cross multiply, and we have 10,000 less than or equal to 2n factorial. What we now want to do is find, remember the goal here is to find the first term to omit from the Maclaurin series for cosine of x. So let's find the smallest n such that this inequality is satisfied. And to do so, we can set up a chart. So let's make a chart of n. And 2n factorial. And let's start computing some values. If n is 1, then we have 2 times 1 factorial, or 2 factorial, or 2. If n is 2, we have 2 times 2 factorial, or 4 factorial, which is 24. When n is 3, we have 2 times 3 factorial, or 6 factorial, which is 720. And if n is 4, we have 2 times 4 factorial, or 8 factorial, which is 40,320. And we notice we have what we want when n is 4. So our first term to omit, and again, the reason why we have that is because this exceeds 10,000, which was our criteria here. Thus, the n equal 4 term is the first term to omit. The n equals 4 term, remember, this was the form for our first term to omit. Plug in 4. And we get x to the 8th over 8 factorial. So we stop at the x to the 6th over 6 factorial term, and that gives us an approximation to cosine of x on the interval minus 1, 1 that will have an error less than 0.0001. So this completes the presentation on the different types of questions you see with error analysis for Taylor polynomials. And again, we see them typically in 3 flavors where you're given 2 of the 3 of these things. You have the actual approximating polynomial to the function, the interval I for x, and your error tolerance. And typically we're given 2 and we have to find the third. It is good to have some practice with these because these are very standard types of Taylor theorem questions.